Okay, hello everyone, and welcome to our first talk after the long summer break and after our panel discussion we had a few weeks ago. I'm very happy to introduce to you Ameet Talwalkar, who is our speaker today. Ameet is a junior professor at the machine learning department at CMU and has a lot of machine learning background. He's the president of MLSys board and helped to also create the MLSys conference. He is also a co-founder of Determined AI, which was recently acquired by HPE. And he works on statistical machine learning with interest in automation, interpretability, and distributed learning. And today we will chat about automating architecture design for emerging machine learning tasks. And Ameet, we're very happy to have you here and very excited for your talk. The stage is yours.
Great. All right. Thanks so much for inviting me. It's really it's nice to be here. And yeah, I'm excited to talk about this work today. Really focused on, I'd say, AutoML for emerging ML tasks. It's an area that my group and I have been thinking about for the last year and a half or so. So yeah, let's dive in. And if you have any questions or anything, please feel free to interrupt me along the way. And yeah, Nick can answer the hard questions because he's here listening as well. But let's see. There we go. Okay, cool. So to get started and set the stage, I want to rewind back to the field of computer vision in the 2010s. And I imagine this is sort of a slide that this graph or one like this is one that most or all of you have already seen, but I think it's worth kind of revisiting and thinking about it. So, right, kind of starting in 2010, ImageNet was this, object detection benchmark that was very challenging and kind of was helping guide the field of computer vision. In 2010, 2011, it was stagnating a little bit. There hadn't been that much progress. And you could argue that the modern deep learning era started in 2012 with the performance of AlexNet on ImageNet, where it kind of absolutely dominated all the other entrants. And soon afterwards, in the subsequent years, we just saw a steady march of progress of AlexNet to later Inception, ResNet, and so on. By 2015 or so, we were kind of matching or even beating. We were obtaining superhuman performance on this really hard benchmarking task, and we were seeing a lot of progress in computer vision. And I'd argue, and I think it's fair to say that most of the progress here was focused on innovations in hand-designed convolutional architectures. Right. So here, for instance, is a picture of GoogleNet, which at least to me looks super complicated and opaque. Right? It's not at all obvious to me just looking at it why this is a good architecture for ImageNet, or just generally necessarily a good architecture. But lots of really smart people spend a lot of time and a lot of compute to hand design and handcraft these architectures to work well, to some extent, really just on ImageNet, but maybe more generally for computer vision tasks, right? And kind of some of the things that they were thinking about in doing this sort of handcrafting of architectures was, there were a bunch of really interesting innovations. So one was the use of repeated cell blocks. So that picture that I showed before of GoogleNet, that really consists of a bunch of these inception modules or inception cell blocks kind of glued together over and over again, right? Ideas like normalization, batch norm in particular, was really important and promising here to improve performance. Co-designing optimizers for these modern architectures also was quite important, right? So Atom being a canonical example here. ResNets became really prominent due to the use of skip connections. And kind of going back to this first point, it wasn't just the use of repeated cell blocks, it was also tinkering with the cell block design itself, the size of the convolutions, what types of pooling, how to connect the different nodes within a cell block. All of these things turned out to be really important. And I think, for example, there were maybe 3 different versions of the Inception module, which really continually improved performance of the GoogleNet architecture, right? So we're seeing a steady progress. And around this time, people started, I think, very naturally to say, okay, well, if a lot of the success of doing well on this ImageNet benchmark is tied to very manually intensive, designing of convolutional architectures, can we sort of automate this process? And sure enough, that's what that started this field of neural architecture search, which to a large extent really focused on cell block design, right? So maybe starting something like, say, the darts search space was really designing a cell block and trying to search through that cell block in an automated fashion to get better architectures. And we saw increasing performance as a result of neural architecture search, further pushing superhuman performance on ImageNet. right? So that was, the 2010s, but now we're in 2021. And there's this question, you could ask of, how important are new convolutional architectures today for computer vision? And on one hand, that's sort of a loaded question. And I think the answer really depends, right? So on one hand, right, there is a lot of work on multi-objective optimization where people want to use neural networks, convolutional neural networks, or otherwise on remote devices or edge devices. And in such settings, right, you want to maintain and preserve high accuracy, but you also need to be mindful of other non-accuracy constraints, inference, memory, energy, what have you. And so they're designing architectures that are able to effectively balance these different constraints is a really hard and promising and open area and highly active. On the other hand, right, you could argue that for kind of more traditional computer vision tasks, where you're really optimizing for traditional metrics of accuracy, that the field has really come a long way and modern architectures are fairly mature at this point, right? And this is something that I've seen talking to practitioners in terms of, they don't see that the pain necessarily for their computer vision tasks is necessarily tied to having a good architecture anymore. It's other things. But it's also, when you think more broadly beyond just computer vision to other problems, other domains, you also see sort of this embracing of the maturity of computer vision architectures. And again, this is something that I see in practice a bunch when talking to practitioners, but I think one really interesting example of this, and this is a paper that a student of mine shared with me just a few weeks ago. This is a paper where it was just published in Nature, I think a few weeks ago, maybe a month ago, something like that. But it's there were computational biologists who were working on some sort of tabular data, I think gene expression data. And in order to make the most out of their gene expression data, they first converted their tabular data into images such that they could thus then leverage these mature convolutional neural networks. And sure enough, they were actually able to get better performance by doing this sort of, clever, but I would argue quite indirect approach of taking advantage of their tabular data. They were able to do better with this approach than directly working on their tabular data. And so on one hand, right, I think this speaks to the maturity of convolutional neural networks that were really designed for these image problems. But it also, I think, is to some extent, I hear about this work and it's kind of alarming. It sort of feels like we're fitting a square peg into a round hole, right? Maybe it's the case that there are applications that are fairly far removed for computer vision where convolutional neural networks very, very much tailored to computer vision tasks are still quite useful. But it seems like, given that there's a huge amount of manpower, invested into developing these networks with a specific task in particular domain in mind, it seems like you could probably do a fair bit better, not doing the square peg round hole sort of approach. And in fact, we have some examples of this already, right? So, there are other domains where we have seen that convolutional neural networks, they either don't work well or they don't work well enough, and people have had to hand design other architectures to work better on these domains. So I think, maybe the most obvious example is with sequence modeling. Convolutional neural networks work okay, especially when you use large dilations, but transformers, we've seen self-attention in transformers to work better. And maybe more exotic applications, and we'll be talking about these latter two later on in the talk as well. One is protein folding. Again, vanilla ResNets work okay, but specialized dilated ResNets have been shown to be better. And recently, I think this is super exciting work, and there was a paper by some folks at Caltech and elsewhere at iClear this year talking about this problem of neural PDE solvers. And here, convolutions work not all that well at all. And this entire paper, which is pretty high profile paper, and I think it's an exciting area in general, was focused on introducing a new architecture based on this idea of Fourier neural operations that led to state-of-the-art performance for neural solvers. So, right, you might argue that, okay, fine, convolutional neural networks aren't always the best, but the combination of convolutional neural networks and transformers maybe together are, suffice for the most part for the applications that we have today. And on one hand, maybe that's accurate, right? For a lot of the modern applications that we're seeing in production, whether it's autonomous vehicles, image search, voice-powered assistance, voice-powered search, right? A lot of these are sort of like image or speech or NLP sorts of tasks where CNNs and transformers are likely to suffice for right now. But I would argue it's pretty short-sighted to the reason there is so much excitement just broadly about AI and about deep learning is for its transformational power, not just for applications that are currently leveraging it today, but by all the applications that could potentially leverage it today, either those that we already know that we could do it, or maybe even more importantly, for applications where we haven't even thought about using deep learning on these sorts of problems, right? And so it's a little myopic to say that, we've solved this problem for a few low-hanging fruit applications or domains, and obviously very, very important domains. But there's arguably many, many other domains that could really benefit from the same sort of technology. And it's not at all clear that convolution or convolutional neural networks or transformers are the right solution for these emerging tasks and domains. And so very broadly speaking, the set of problems that I'm interested in the area of automation and AutoML is how can we help users apply neural networks on their emerging tasks, on tasks that are just starting today to be interesting, or which we think we won't even realize that we can apply deep learning or other ML techniques to them in the next few years, right? So rather than focusing more and more on improving performance on computer vision or NLP, which are very important, and even small gains there are very important for for industry and for a wide range of applications, I want to instead focus on the set of problems where there is less less manpower to actually devise handcrafted networks, and to see how well can we go from 0 to 1 in terms of making machine learning or deep learning actually useful for these applications. So the talk is going to be divided into 2 parts. The first is based on recent work that was just accepted at NeurIPS called XD operations, which is a particular, broadly speaking, it's devising a new search space that is designed to work well on a diverse set of tasks or emerging tasks. And then the second part is a new benchmarking suite, which is again motivated by this problem of diverse or emerging tasks. So I'll pause here for a second though to see if there's any questions before I get into the details of the technical part. Okay, so I'll move on talking about XD operations, and this is joint work with my student Misha, former students Nick and Liam, as well as collaborators at Stanford, Tree and Chris. Okay, so let's go back to a few slides ago, right? These are a few of these examples where we'd already seen that vanilla ResNets or vanilla, CNNs more broadly don't quite work as well as you want, and people have had to come up with handcrafted networks that were tailored to these specific new domains. And the thing that I want to point out here is that in all 3 of these examples, and I think this is a trend that holds, maybe not always, but beyond just these 3 examples as well, is that the key human innovation was on designing new operations, right? And so, right, in all 3 of these cases, existing backbones and effectively different variations of ResNets were used for all of the ultimate architectures that ended up working out really well. What changed was moving away from a convolution to a new operation that was specifically designed and tailored for the application of interest. So in sequence modeling, it was, instead of a convolution, it was self-attention. For protein folding, it's dilated convolutions. And for solving PDEs, it was this FNO operation, right? And so I'm calling this problem, this task of architecture transfer, where you rely on existing backbones. And we're gonna, throughout this talk, rely on some version of a ResNet. But you rely on the ResNet and basically want to see if there's an operation that is different and better than a convolution for your particular domain-specific task. And the question is, can we automate this process, right? So instead of having to, human experts have to handcraft these new operations based on deep knowledge of the domain, but also a fair bit of knowledge about neural networks, can we somehow automate this architecture transfer task to learn these new operations, right? And so in specific, again, to reiterate, our goal is to learn a task-specific per edge neural operation. So what I'm showing here is just a visual schematic of a very simple neural network. And right, the idea here, if I was using a CNN, this op24, basically the operation going between node 2 and node 4 would be a CNN. Now, instead, what I want to do is have this be some sort of parametrizable operation that I can learn from data, right? And so the question is, what operation should I consider? Right? What operation should I choose from if I want to move beyond just a CNN, right? And so one thing you could do is, choose from a discrete set of existing operations, right? This is kind of what a lot of neural architecture search does. It lists a set of operations, typically these vision operations, different types of pooling, different types of convolutions, an identity operation. You could potentially add to this discrete set a small handful of operations that we already know to work well for other domains. So you could add F&O, you could add certain type of dilated convolutions if you wanted. But the problem with this sort of discrete approach, and in particular, just really leveraging on the existing set of operations, maybe less discrete and more leveraging the existing set of operations that that we already know about, is that we can't discover novel operations. And kind of the underlying hypothesis here is that we're really just scratching the surface of the set of domains and tasks on which we want to apply deep learning. And we've really been optimizing for a certain, small number of domains and tasks. And it's not clear that those same operations necessarily naturally transfer or applicable to these new sets, to these new domains, right? And so what we really want is a more general space of operations that ideally is backwards compatible, right? So ideally we'd like a really, we'd like the biggest set of operations possible, right? We'd like a space of operations that include all the named and known operations that we've used before, but include as many new, but the space should be as expressive as possible and include many, many other operations as well. Of course, the trade-off here is that the more expressive something is, the more expensive it's going to be to actually identify a good operation from this big space. So obviously there's this trade-off between, efficiency and expressiveness, but, we're going to get to that in a little bit. But so just at a high level, what we're doing with XD operations is trying to move more towards this expressivity perspective, right? We introduce a continuous space of operations, which is in some sense backwards compatible. It contains several named operations, or in other words, operations that you've heard of before. Average pooling, different types of convolutions and dilated convolutions, this F&O operation, certain subsets of graph convolutions for fixed adjacency matrices, I think convolutions composed with permutations, right? So it contains a bunch of operations that you've heard of, but it's also, it's continuous. So it contains a bunch of, an infinite number of operations that have not been explored before either. Importantly, it's also differentiable. And we'll talk a little bit more later about how you actually might use XD operations if you were a practitioner. But ultimately, just fast forwarding and previewing, the idea is that we are going to want to learn which operation to use from the set of XD operations using some version of gradient descent. So the fact that this is a differentiable parameterization is very appealing to us. Okay, so I will, before I go into how you actually use XD operations, I want to at least give you a little bit of an overview of how we construct them and how we're sort of balancing between expressivity and efficiency. And to do that, I'm actually going to go back to talking about convolutions. So I know I talked before about how convolutions are limiting. They're very much focused on computer vision. They're probably the wrong operation for various new emerging tasks. That said, they still are a very nice starting point for us to, they're a nice operation that we can generalize and which we choose to generalize for XD. So they're the building block for XD operations. And there's to kind of build up to what we're doing with XD, I need to tell you a little bit more about convolutions. So the kind of first thing to note is that, right, most of the common operations that people use in computer vision are actually some form of convolution. So this is how we sort of get our backwards compatibility. If we're starting by saying that XD is a generalization of convolution, we first need to say that all common vision operations are themselves all convolutions. So that's kind of the point here. Aside from max pooling, which you can't easily write as a convolution, I would argue that the common operations that people use in vision, the ones listed on the slide, are in some sense, can all be expressed as a convolution. And some of them are sort of like the identity, say, is or the zero operation. These are kind of edge cases of convolutions, but nonetheless, they are a edge case or a very reasonable type of convolution. All right, so that's point one. Point two is that convolutions generally have some very nice properties. And so first and foremost, the nice property that convolutions have is that they can be expressed as linear operations. And so what do I mean by that? Well, so imagine you have an image, a 100 by 100 image, and you have a 3 by 3 convolution that you want to apply on this 100 by 100 image. And the filter weights for that convolution are expressed, are represented by some matrix or vector W, right? you could then equivalently express the convolution of this filter on this image as a matrix vector multiply. The vector is X, which is just the vectorized version of the image. So if I have a 100 by 100 image, I just stretch it out. And the matrix A is the linear operation that is performing this convolutional operation with the filter weights W on this vectorized input X. Okay, this is just a known fact about convolutions. Another important known fact about convolutions is that this matrix AW itself is very special in the sense that it can be diagonalized by the discrete Fourier transform. And this is really nice because DFTs are efficient matrices. And what I mean by that is, right, so if AW is, let's say it's an n by n matrix. If AW is an n by n matrix, an arbitrary n by n matrix can be stored and applied in O of n squared time in space, right? It can be stored in n squared space and applied in n squared time. But AW can be represented and applied in O of n log n bits in time. So in that sense, it's efficient, right? And so kind of the key idea behind the XD operations, or the space of operations that we're considering, is can we still preserve this efficiency of convolutions while also being more expressive? And the way to do that, very intuitively speaking, is to replace these DFT matrices, which appear 3 times, right? The F inverse in the diag of FW and at the end F. Can we replace these 3 F matrices with an alternative, more general family of efficient matrices? And that's kind of exactly what we do. And so I don't expect this equation to make too much sense to you, but the key thing I want to point out here is that, right, I'm defining K, L, and M on the right-hand side here as, I'm saying that these are arbitrary efficient matrices, and I'll tell you on the next slide a little bit more what I mean by that. But if I define, L and M to equal F, and I define K to be F inverse, then the XD operation has just recovered a convolution. But if I say that K, L, and M can either be F or F inverse or one of many other efficient matrices, then this XD operation has generalized the convolution, right? And if the K, L, and M are efficient in the same way that the DFT is efficient, then there is hope that we have a better trade-off here between efficiency and expressivity in terms of the operations that we can consider. Right, so the next question is, what family of efficient matrices should we use? And for this, we build on, this is, I think, a fairly active area of research. And we build on, and this is, some of the interesting work in this area is being done by our collaborators on this XD work, Tree, Chris, and their collaborators at Stanford. But they recently introduced this set of matrices called kaleidoscope matrices, which they were able to provably show can express any efficient matrix vector operation. So that includes DFTs, and we kind of talked about that on the last slide. Right? You can take these general matrices and define them to be F or F inverse, but they also include many other type of efficient, all other efficient matrix, all other operations that satisfy this notion of efficiency. So sparse matrices, low rank, permutation, DCT, wavelet transforms, and so the idea is that can we generalize so the idea again in a nutshell is, can we replace the DFT with K matrices in the expression of convolutions? And can we try to learn these K matrices, K, L, and M, as part of, along with the model weights when using XD operations, right? So we call architecture parameters these matrices K, L, and M. And these are things that we want to learn alongside, right? So these are architecture parameters in the same way that the mixture weights are architecture parameters, say, when you're using darts or when you're thinking about darts. And again, the benefit here is that at least asymptotically, we're able to preserve the efficiency of convolutions in terms of operating on and storing these matrices. In practice, there are some additional constant costs, and we'll talk about that a little later. So we're not exactly as efficient as using just a vanilla CNN, but asymptotically we are, and we think that there are ways to be more and more efficient. And this is right. This is early and ongoing work. We think that there's room for improvement in terms of efficiency, and in terms of expressivity, as we talked about earlier, we're able to recover convolutions. Most other common vision operations, but also many, many other named operations and an infinite number of operations that may or may not be useful for different emerging tasks. Okay, so that's the idea of where this this family of XD operations come from. What I want to talk about next a little bit is how you actually use these operations. How would a practitioner, what does the workflow look like to actually use these? And to do that, right, the hope and the idea, the hope is that it's not going to be much different than what people are doing today, but it'll be useful, right? So how might people, so instead of telling you immediately how to use XD, let's start by reminding ourselves of how a practitioner might use a CNN, right? And so we already talked about how those computational biologists might first take their data, their tabular data, and transform it into an image. But let's say they have, they have data that applies to a CNN. They have to do whatever transformations that they have to do. But then the first step is to choose a popular CNN, say a ResNet. And that's, again, what we're going to be talking about next in our experiments. Then you want to train your model weights using SGD, mini batch SGD, Atom, some SGD-like method. And then finally, you want to evaluate and tune as needed, right? There are hyperparameters related to the optimization routine, related to the regularizers you're using. You want to tune those hyperparameters and then you're done. Okay, so those are the same basic steps as well when you want to use XD operations with a few tweaks, which I'll explain next, right? So first, in the first step, now instead of just choosing a popular CNN, what you're doing is you're just relying on the backbone, right? So instead of using a ResNet, you're going to use the ResNet positions, which are a fixed operation, with this parametrizable, I always have trouble saying that word, this parametrizable XD operation, right? So what this means is, if you're just using a ResNet, the only set of weights you have to learn are the model weights, right? If it's a fully connected layer, it's those, for any fully connected layer, it's just the weights of that layer. For any convolutional layer, it's the filters themselves. If you now, though, replace the CNN with XD operations, you both have to learn the architecture parameters, basically what XD, which is going to determine what XD operation you're using from the family of XD operations. And then you also have to learn the model weights as well. But as we talked about before, XD operations are differentiable. So you can also use SGD in the same sort of way, simultaneously train architecture parameters along with the model weights, both using SGD. And then finally, you're going to evaluate and tune as needed. And at least in our experiments, the only thing we do is additional tuning on is the optimizer settings for the architecture parameters. So, following the same, slightly more hyperparameter tuning, but largely the same routine that you would perform otherwise. Okay, so next I want to, before I go into experiments, there's one more thing I want to say, which is, providing a little bit more context of how this relates to other NOS research. And I think that there's some ways in what we're doing is building on a lot of the cool things that the NOS community has come up with over the last, 4 years, however long it's been. But in other ways, I think we're doing things that are kind of different. So one way in which I think we're different is just generally the focus is on the search space, right? I think what we're arguing is that focusing on discrete search spaces that are largely motivated by computer vision tasks is very limiting in the context of actually making progress on emerging tasks. And so what we wanted to do is, we wanted to introduce a continuous search space that contains all, nearly all of the discrete NOS operations, but infinitely many more, right? So this is the picture that we've seen. We've talked about this. Aside from max pooling, we pretty much contain everything you probably would consider in a standard computer vision-based NOS approach. The second point, I think this is a point of similarity, is that we are leveraging weight sharing, just like many other NOS methods do, right? So weight sharing was initially, used for continuous relaxation NOS. And again, for those of you who are not familiar with this, that's okay. This is sort of a detail. But the point is, we are using weight sharing to simultaneously, just like standard NOS methods, learn architecture parameters and model parameters. And then finally, another area where we're different from classical NOS, but I think this is kind of a line that's being blurred in NOS in general, is that we are performing single stage learning. So in classical NOS, right, when it was first introduced, the idea was that the goal of NOS was to search for a good architecture. Once you find that good architecture, you do a subsequent step where you train that architecture from scratch on your data. And so that's sort of this two-stage learning. What we're doing here is we're in one shot learning the architecture weights and the model weights, and we're calling it a day, right? So you could technically say, well, that doesn't follow the strict paradigm of neural architecture search. And in some sense, you wouldn't be wrong. But I think maybe more importantly, that seems like more of a technicality in my point of view. I think the more important thing is the underlying motivation and the question that we're trying to answer, which is how do we automate the process of architecture transfer for emerging tasks? And I think this is an important problem. And whether you do this, whether you're solving it via NAS or by proposing a new model family, which in many ways looks like NAS, but in a few ways doesn't, I don't think that matters one way or the other. I think, solving the problem kind of is more important. Okay, so I'll pause there again for a second before I talk about some of our experimental results, just to have a sip of water, but also see if anyone has questions.
Yeah, so I have a question just to make sure that I understood this correctly. So you learn the architecture parameters jointly together with the weight parameters. So you don't have this bi-level object optimization that you have on darts, right, where you alternate between optimizing weights and optimizing architecture parameters on the validation data set.
So I guess, no, sorry, that wasn't exactly what so with darts, for instance, we are doing, the weight sharing part, it is still potentially an alternating sort of thing. What I meant in terms of what I meant in terms of single stage rather than two stage is that for something like darts, what you do is, you do weight sharing, you do this alternating optimization between architecture parameters and weights and the model weights. But once you're done with that process, what you do is you discretize the architecture weights, you identify the best architecture, from your architecture weights, and then you do a second step altogether where you retrain a model from scratch using the architecture that you've identified from the learned architecture weights. And what I'm saying is we're not doing that second stage. I
see. Okay, that makes a lot of sense. So, but the architecture parameters are still optimized with respect to the validation performance, right? You don't use the.
Yeah, I actually can't remember if that's a separate question of whether I think that is the case. I think you could potentially do it all with training with one set of data, but yeah, my point here is not. Yeah, I think we're still using validation data, but Nick, you can correct me if I'm wrong.
We're jointly learning them on the training data.
Okay, so we're doing ERM. We're not using. Okay.
Okay.
But I guess I feel like in the NOS community, people have been doing both of those things recently. Yeah, I guess that wasn't the thing that I was trying. I feel like that's already people have done one way or the other. For me, it was more of this, do you do this post-processing stage? And we are not doing that.
Yeah, so maybe another one. So if I understand you correctly, what you essentially learn is this matrices KLM, right?
Yeah.
And this matrices KLM somehow reproduce this matrix AW, right?
Yeah. Well, now, or they reproduce, they reproduce an alternative.
They define a matrix AW. In a sense, I would argue that, what's the difference between a convolutional network and a fully connected network? Basically, you do two things. First, you don't connect all the neurons between layer L and L+1. Second, you have weight sharing. So you can say that this matrix AW is basically a special kind of, connection between layer L and L+1, where you apply these two criteria. And in this way, you put it back into the original way how you define a neural network. Well, not fully connected, which means in AW, you have a lot of zeros, and weight sharing, which means that you have a lot of repetitions within AW. And what I think what you do here is somehow do something in between the two extremes. So what you do is that you make somehow the weight sharing configurable. In fact, you don't commit anymore to weight sharing. You can, because if I'm not mistaken, maybe correct me, but I think AW contains the weights. So it's not that you learn KLM plus the weights, but the weights are implicitly contained in KL and M, right?
The weights are explicitly contained in
implicitly.
No, so we have a separate we have W separate. Like, so if you look at that expression, W, like we are decoupling K, L, and M from W. I mean, I get your broader, I think your broader point is one I don't have an answer to. And I think it's a very interesting question of whether, like, is there another equivalent way of expressing what we're doing in terms of, yeah, is there another equivalent way of expressing it in what we're doing in terms of using other language or other kind of concepts that people have already looked at? The answer could certainly be yes, and if so, I think that'd be really neat. But I don't have a.
Not necessarily. The question was really a comprehensive question, so I understand well what you're doing. So basically, in the backpropagation step, what you learn is KLM, and you say also W. Okay, so
yeah, but so the W, like, so right in the same way that, yeah, the KL and M are the architecture weights, the W are the model weights, and we're jointly learning them in terms of there's one objective, but practically, you know, you can do alternating optimization between them.
Okay, yeah, yeah, maybe I have to look at that more detailed, but okay, yeah, very interesting.
One other thing I would say is that there, right, one thing, when we first made this connection between, you know, oh, can we generalize a convolution in a certain way? Our idea was initially to just conflate the weight, the model parameters and the architecture parameters. So then you would have a simpler looking form, and it would just be one, you know, you just have one K matrix that you would learn. There were a bunch of reasons that was a less attractive, from a kind of computational perspective and expressivity perspective, that was just a less attractive direction to go. So we were pretty explicit about decoupling these K matrices that we wanted to learn from the W, or from the model weights that we want to learn.
Okay, so so this approach explicitly commits to weight sharing. Yeah, so this is still embedded, and the approach has not the freedom to skip weight sharing, so to say.
I mean, computation efficiently wise, I don't, yeah, it's, I guess I don't want to say maybe there was a world in which we could get away from it, but no, at least the way we're thinking about it right now, that is a pretty big, yeah.
Okay, thanks.
Yeah. Okay, so thanks for those questions. Let me talk a little bit about some of the experiments to kind of explain what, you know, intuitively what we're trying to do here. And maybe I'll start big picture again, just to remind everyone what the goal of all of this is, to say, okay, you know, if I'm a practitioner and I have a new problem, I could either start with a, you know, my options are twofold right now. One, either use an off-the-shelf architecture, a ResNet. Two, hire a deep learning expert to come up with a bespoke architecture that works well on my task. What we want to do is have option 3, which is not start from scratch, but start with some, you know, do automated architecture transfer. So start with a ResNet, but instead of using CNNs, use an XD operation, use this parameterizable XD operation instead of a CNN, and automatically learn an architecture that is, you know, ideally nearly as good as what the option 2 would be, which is, you know, an expert actually designing a bespoke architecture. And what we're going to show in these experiments is, the first one is kind of a warm-up, but the second 2 are going to be settings where we can compare the vanilla ResNet to the hand-designed architecture to XD. And we want to, you know, ideally we want to be much better than the vanilla ResNet and at least close to the hand-designed, right? The hand-designed architecture, with the idea being that for the few applications we've looked at so far, they're ones that are both not computer vision, but there have been handcrafted architectures for them. But for, you know, a huge number of emerging applications, there won't be existing handcrafted architectures, and so XD could be a replacement for that. So that's the intuitive idea. The first application is this warm up of starting with Safari 10 and permuted Safari 10. The idea is simple, which is that, you know, Safari 10 is the very, very simple image benchmark, as you guys all know. In some sense, convolutions are the right, CNNs are the right architectures and the right operations for these, for this type of data and for this problem. But what happens if we take SAFAR 10 and permute the rows and columns of it? So you go from the first column to the second column. It's the same image, but the rows and columns permuted. It makes sense that taking advantage of local structure, as convolutions do, wouldn't make sense once you do this permutation. So in some sense, the quote unquote right operation would be to undo the permutation followed by a convolution. It turns out that that actually is an XD operator. It's in the set of XD operations. But the question is, how well do XD operations do relative to CNNs here? Granted, this is toy warm up, but it's a good sanity check. So the first thing we're doing is actually vanilla SAFAR 10. And again, this is not the problem we care about. We're not focused on image tasks. Precisely, we're focused on emerging tasks, but we want to be backwards compatible, right? We know that convolutions are in XD, so we want to see how well we do. The third baseline we try is a baseline where we include, the darts relaxation. We include all the discrete set of operations that are included in the Dart search space. We try, we tried two backbones, LayNet and ResNet 20. CNN is really just LayNet or ResNet 20. The darts relaxation are these guys with the different operation choices at each edge. And then XD is what we've been talking about. The point here is that we're backwards compatible. The goal is not to be better, but we don't want to be significantly worse. And at least on these two, on this setting, we're if anything, slightly better. The next question is what happens when we now permute. And this is, the first promising result. Unsurprisingly, we see that CNN and darts, because they're both convolutional, their performance suffers drastically. What we see is that, with XD, we do significantly better, right? And you can kind of, Nick made this cool GIF where we're based on inductive bias of convolutions, we're forced to rely on local patterns, right? This is the convolutional filter, and it's just going through the image. This is the alternative operation on the right that we're learning via XD. I can't tell you much about why it's doing what it's doing beyond the fact that it correctly is not focused on local patches, which makes sense given that we've introduced this permutation. All right, so the next application is more of a real application is this the neural PDE solvers that we talked about before, and just a little bit of background on this problem, right? So the idea here is that the field of developing PDE solvers is a very, very rich field in scientific computing and applied math and so on, and traditional solvers actually work really, really well. So the goal here is not that the goal actually is to, if anything, match the end results of these traditional solvers, but to do it more quickly. Right, so the issue with traditional solvers is that they're slow, especially at high resolutions. Right, so as a canonical example, imagine the idea is often that you want a solver to map from some set of initial conditions to conditions sometime later. Right, so you start with conditions of an ocean surface at time 0, and you want to predict the conditions at 50 seconds later. The idea is you might want to solve this PDE multiple times for different initial conditions, different initial ocean conditions. And so given infinite time, these traditional solvers maybe are okay, but you want to do this more quickly. And especially if you want to solve the same PDE with different initial conditions multiple times, there's this idea of, can you instead learn a neural network that maps from initial conditions to a solution, and then given a new initial condition, only requires a single forward pass for inference, which could potentially be orders of magnitude faster than calling the traditional solver each time for a new set of initial conditions. And sure enough, right, and granted, this is, I think, early work. I don't think this problem has by any means been solved. It's also worth noting that that there was exciting work at by folks at Caltech and their collaborators at ICLR this year, showing that indeed you could make some progress along this direction. You could match the accuracy. You could preserve quality of the solution even at higher resolutions, and be much, much faster, right? And it's important to note that these neural solvers are still relying on traditional PDE solvers to generate the data, and then they learn the mapping, and then things are faster in inference time. But so that's kind of the background of where we are, and we use the same experimental setup as was done in this ICLR paper. We also we tried a few different competitors. So first we tried a standard CNN, and we use the same data that they started with. So we tried a standard CNN to learn a solver. We also tried two classical NOS methods. The y-axis is error, lower is better. x-axis is you're running the same version of the problem at different resolutions, because there is this question of how well you do as you go to higher and higher resolution. And ideally you want to be flat. If your performance gets worse, meaning the slope is going up at higher resolution, that's bad, right? And so all three of these methods are performing fairly poorly. The FNO neural network is performing much better. So this is a very good result. And this is kind of the main result from this iClear paper. And then this is what we found with XD, right? And so there's a few takeaways here, right? So one, the family of XD operations contains both convolutions and FNO, yet outperforms both of them. Two, it is worth noting that our XD network is slower than the FNO network by nearly an order of magnitude on inference time. Yet it's still significantly faster than traditional solvers. So it's still, it still follows that same story, but it is worth noting that it's not a fully apples to apples comparison, and that we're slower. And finally, this is for one PDE. We look at all the other benchmarks used in the FNO paper, and we get similar results where we match or beat FNO. And so we're really excited about this result, partly because, right, this is actually an important problem, and this is quite an important problem that there was evidence just in this year of someone needing to spend a lot of time to the point that it was worthy of a well-regarded iClear paper to develop a new architecture for this new emerging task. Yet we were able to, we had started thinking about XD before we had heard about FNO. We discovered after the fact that this FNO operation was contained in the set of XD. So it wasn't in any way, but it worked quite well. So that was sort of really cool. I guess the other caveat here is that these are early results, right? I think that the thing that we're doing next that we're also really excited about is actually talking to people who focus on PDEs and PDE solvers to kind of get more real world experience and vetting from people who are actually experts in this field. But this is, I think, a pretty promising result. And then finally, I'll quickly talk about a third application, which is this protein folding application. The particular problem here is predicting pairwise distance between amino acid residues. And right, I'm not an expert in this area, but my understanding is that this particular prediction problem is a key component of pipelines like AlphaFold, which themselves are gaining huge amounts of popularity for their performance in predicting protein function. And in particular, we're working with this one benchmark. It's this PDNet / I don't know how to pronounce this, PSICOV benchmark. It's freely available training data and test data. They also propose a hand designed architecture to improve upon a ResNet. It's a custom dilated ResNet with cyclically increasing dilations across blocks of the ResNet. Right. So again, story is similar here, where we want to do better. We know that a vanilla ResNet doesn't work all that well. We want to see if we can get close to matching the performance of a handcrafted architecture. In this case, this dilated ResNet. All right. So what do the results look like? There's a little bit to unpack in this plot, right? So y-axis is some measure of error. We're using the same experimental setup and reporting metrics as in as proposed by the benchmarks. I'm not going to go into details, but we're not changing anything. All that matters here is that lower is better. The hand design architecture that they introduced is this 200 plus layer ResNet. And that's what we're showing in the dashed line. We didn't want to train, for computational reasons, a bunch of networks that were that deep. So we instead, right, we're still comparing against this as kind of the watermark number to try to get close to, but we wanted to look at various types of networks with smaller depths, ranging from 4 to 34. So that's what you're seeing in the x-axis. So first we tried, training vanilla ResNets and these dilated ResNets at smaller depth. And what you see is that the dilated ResNets do beat vanilla ResNets for the most part. And intuitively, the idea is that if we extended the x-axis out to, sorry, I can't remember, it's 256 or I can't remember, whatever, 200, whatever it is, it's blocked by the people on the Zoom screen. So I can't see my own legend. But that blue line would eventually converge to the dotted gray line if we increase the depth to be enough. Right, so those are the first two baselines. We then tried two NOS methods. Auto Deep Lab performed quite poorly. Using actually darts operations performed reasonably well here. And then we tried, ResNet XD. And so the takeaways here are, kind of similar. We outperform dilated and standard ResNets at all depths for the most part, except for very short depths. We also auto DL doesn't do well, but we also outperform Dart's operations. And we in fact improve upon state-of-the-art for this deeper 258 dilated ResNet. Caveat, it's worth noting that, we beat their reported result. When we retrain our own dilated ResNet, we get a slightly better number. And so I think the point here is less who's getting state-of-the-art. It's more that, again, in a very automated way, just plug and play using this XD idea, we were able to get something very competitive with a hand-designed architecture. It is also the case though that, we're depth 34 rather than 258. So you can imagine that that number would go down if we trained it longer. Okay, so that's kind of a summary of XD. I'm gonna quickly go over this because I want to spend the last few minutes on NOSBench. But the point is that, I think we're really excited about this work, that there are open questions. How do we speed up XD operations, make it more efficient? Actually, this is what we're talking about. Oops. Right, so one issue is that we're dealing with, research grade code versus highly optimized code, things like CUDA. The other thing is that, maybe there are other approximations that we can make. So are there alternatives to K matrices that we can use? Is there some way to use mixture relaxations of discretized search spaces to speed things up? One of my students, I think Junhong, who's on here, is looking into that a bit as well right now. Other questions though, can we improve expressivity, right? XD doesn't include self-attention. It doesn't work for, it doesn't necessarily work well in dynamic graphs. And this last question, which is a good segue into NOSBench 360, is that an apples to apples evaluation is hard, right? Like, we picked some applications which suggest that what we're doing is working well, but doing this kind of systematically and fairly across a diverse set of applications is, kind of necessary to really guide research in this direction. And so that kind of naturally brings us to NOSBench 360.
I mean, one question. There's like one open question before you continue, maybe.
Yeah.
That would make sense.
Oh, yeah, sorry, what's the question?
Yeah, yes.
I can ask. Thank you for the great talk. So I'm not familiar with the other applications, but for the CFAR, permitted CFAR, of course, CNNs are not going to work because you are destroying the locality and the translation invariance property that CNNs are actually focusing on. So I'm curious, what kind of property are you catching with these XD operations in non-vision or any kind of applications?
So I agree with you. I mean, the way we present it in the paper is we say we have 3 applications in our paper. One is PDE, one is this protein folding, a third one is music modeling. We don't even call this SAFAR 10 an application. It's absolutely designed to make CNNs look bad, and it's also not a real, like, permuted CNN is not, permuted SAFAR is not a real data set or a real problem. It was more of a warm up to, in a setting where, it's kind of like in a simulated setting where if you can't show that your method is working better in a simulated setting, what's the point of trying it in real settings? And that was kind of the point of the SAFAR 10. Absolutely, like, there's no reason to expect CNNs to work well there. They're kind of, the problem was adversarially chosen so that CNNs won't work well. But there's still a question of, is XD doing anything? And the answer,
in other applications, do you have locality and translational invariance property in the data?
I don't know. I mean, partly that is the point. I mean, you might not know ahead of time exactly what properties you want. If you know exactly what properties you do and don't want to preserve in your data, and you know how to encode them into either an operation or more generally into the architecture, great, you can do that and handcraft your own architecture. But if you don't know that a priori, how are you gonna, right? The question is, can you automatically pick up on some of that?
And what property are you picking with the XD operations instead?
I guess I mean, a negative answer to that question is I don't know exactly, like, being able to interpret each of these operations that we pick up and explaining why it's the right application for a particular, or right operation for a particular application is something maybe that should be added to ongoing work. Because I think that would, like, the interpretability aspect of these operations is completely lacking right now. So that's the question. I don't have a good answer to that. But intuitively, the idea is that we're making less inductive biases in terms of what you may or may not want to pick up on, and we're trying to learn that from data.
Thank you.
Yeah. Okay, let me spend 2 minutes talking about Nussbaum 3. I mean, there's a lot of details I could talk about with it, but I think the high level point is pretty clear. Right, so kind of what we've realized in part working on XD is that NOS evaluation on emerging tasks is hard, right? You need to curate a representative suite of tasks. You need to perform apples to apples comparisons. And I think crucially, it's important to evaluate not just search methods, but search spaces, right? So I feel like 4 years ago, there was we were lacking in rigor in terms of evaluation generally. The NOS benches have been a huge, huge boon to making things more systematic and lowering the computational barrier. But one thing that I'd actually be really curious if people have other opinions about this, because it's something that I'm like, the best thing about the NOS benches in my mind is that you don't need to be Google to be able to run NOS experiments, because you just look things up. The pre-computing aspect of it is amazing. The downside of the pre-computing aspect of it, though, is at least the way that they're currently built, as far as I understand, they're sort of implicitly, assuming a specific search space, and they're evaluating just the search methods. And kind of a big part of the argument that we're making is that, and I think other people are starting to make this too, is that search spaces matter a lot. How expressive your search space is really, really matters. Especially if you're looking at tasks that are maybe not a lot like computer vision. So we need to be able to evaluate on, search spaces and search methods jointly. How to do that efficiently is still a question. I mean, our answer to doing that is to come up with tasks that are not too expensive to compute, recompute every time you want to do it. But obviously that's more expensive than a lookup table. We have not figured that aspect of it out yet. But anyway, so the point of Nussbaum 360 is to kind of address all three of these things. I'm going to go quickly over this. We have, again, I think there's more tasks that we can and should add over time, but we're trying to be diverse in terms of data dimensionality and size, problem type, application domain. In terms of apples to apples comparisons, we want to, compare, we define specific computational settings and baselines. And I think the idea here is we say, all right, if you're an end user and you're light in terms of your computational ability, you have the resources to train, say, one default wide ResNet, or maybe you're heavier in your ability, you have more resources, you can do hyperparameter tuning over this wide ResNet. We want to compare things under each of these two regimes. And so we want to make sure we're different methods, whether it's these baselines or new search methods or NOS methods or whatever they are using the same sort of resources. And then there's a question of how do you do this evaluation? There are issues with just default taking ranking. Performance profiles are I think are a better way to do this. I don't really have time to talk about this, so I'm going to stop. But basically, the main contribution I think is setting up this benchmarking suite in order to convince ourselves and hopefully others that there is some validity and some usefulness out of working on this benchmark. We've done preliminary sets of experiments on different competitors with appropriate baselines. We have some results. I guess I don't really have time to go through this, so I'm going to skip that. But I think we have some non-trivial and interesting results that suggest that more work needs to be done to, maybe not surprisingly, more work needs to be done to do well on this diverse set of tasks. And there's more work to do. And I'll stop and just thank everybody. And I just want to acknowledge my collaborators and especially the students who led this work, Misha, Nick, and Rembo. And yeah, happy to answer more questions, and all of our papers are you can find them on my website.